Welcome to the next lecture on applications of derivatives. So, in this lecture we will learn how to find the equation of the tangent line and the normal line at points on a curve, and then we will see some application of that. We will start with the equations of tangents and normals. So, suppose we have a curve, and if we look at this point, say P, whose coordinates are x comma y, and we have this curve is y equal to some f of x. Now, the tangent line to this curve is the straight line passing through this point x comma y, whose slope is, so slope of the tangent line is the derivative dy dx at that point at P. So, this we have seen that because if we look at any 2 points on the curve and join the line segment, the line joining those 2 points, and if we take the limit as the point q approaches P, then we get the derivative. The slope is nothing but the derivative at this point P, and the normal line, this is the tangent line, and the normal line is by definition the line which passes through this point again and which is perpendicular to the tangent line. So, this is the normal line. So, what we know is that slope of the tangent line at some point, say x naught y naught, is the derivative dy dx at this point x naught y naught, which is also equal to f prime at x naught if y is given as a function of x, and therefore, the slope of the normal at x naught y naught is minus 1 by this dy dx at x naught y naught. So, now to write the equation of the tangent and normal, recall that equation of the line passing through some point x naught y naught and having slope m is given by y minus y naught is equal to the slope m times x minus x naught. This is a well known formula for the equation of line in the point slope form. So, therefore, the equation of tangent at x naught y naught, let me call this point P, is y minus y naught is equal to, slope here is the derivative dy dx at x naught y naught times x minus x naught. And the equation of normal at the point x naught y naught is y minus y naught is equal to minus 1 by dy dx at x naught y naught times x minus x naught. If this dy dx at x naught y naught, this is non-zero. Now, what can happen is, if we look at, say, this circle, let us look at circle whose equation is x square plus y square equal to 1. So, the problem is find the equation of the tangent line at a point x naught y naught on the circle x square plus y square equal to 1. So, if we look at this equation, x square plus y square equal to 1, this implies 2x plus 2y dy dx, this is equal to 0. This implies the derivative dy dx is equal to minus x over y if y is not equal to 0. So, for every point except if y is 0, we get these 2 points 1 comma 0 and minus 1 comma 0. If y is not equal to 0, we have a point except for these 2 points. So, therefore, if y naught is not equal to 0, the slope of tangent at x naught y naught is m is equal to minus x naught by y naught, and therefore, equation of the tangent at x naught y naught is y minus y naught is equal to the slope minus x naught y naught times x minus x naught, which you can also simplify and write as y naught times y minus y naught plus x naught times x minus x naught equal to 0, or which is same thing as writing x naught x plus y naught y is equal to x naught square plus y naught square, but x naught square plus y naught square is equal to 1. So, we get x naught x plus y naught y is equal to 1. This we have derived if y naught is not equal to 0. Now, clearly here you can see that if we have y naught equal to 0, we have these 2 points on the x axis. Here the tangent line is, the equation is x equal to 1, and here the tangent line is x equal to minus 1. So, here what happens is that the tangent line is vertical. So, at the points 1 comma 0 and minus 1 comma 0, the equations of the tangents are x equal to 1 and x equal to minus 1 respectively. So, here what happens is that the slope of the tangent line is infinite. So, if the slope of the tangent line is infinite at the point x naught y naught, then the equation of the tangent is x equal to x naught. Now, we will look at some examples on finding the equations of tangent lines and normal lines. Second example, find the point at which the tangent to the curve y is equal to square root of 4x minus 3 minus 1 has slope 2/3. So, if we look at y equal to square root of 4x minus 3 minus 1, dy dx is 1 by 2 square root 4x minus 3 times 4, that is 2 divided by square root of 4x minus 3. So, slope of tangent at x comma y is m is equal to 2 divided by square root of 4x minus 3. We have to find the points where the slope is 2/3. So, therefore, we have to solve for 2 by square root 4x minus 3 is equal to 2/3. This implies 4x minus 3 should be equal to 9, and that means x is equal to 12 by 4. So, x is 3. So, we get only one value of x satisfying this slope is 2/3, and when x is equal to 3, y is equal to square root of 4 times 3 minus 3 minus 1. So, this is y is equal to 2. Hence, the required point is 3, 2. Next problem, find points on the curve x square by 4 plus y square by 9 equal to 1, at which the tangents are first parallel to the x axis and next points where the tangents are parallel to the y axis. So, this is in fact if you recognize this as an ellipse, you can easily see that this is an ellipse and these points are 2, 0, minus 2, 0 and then 0, minus 3 and 0, 3. So, from the figure you can see that the points where the tangent will be parallel to x axis are these 2 points and the points where the tangents are parallel to y axis are these points. But let us try to find this using what we have learnt just now. So, we are given x square by 4 plus y square by 9 is equal to 1. This implies if I differentiate with respect to x, 2x by 4 plus 2y by 9 times dy dx is equal to 0. This implies dy dx is equal to minus 9 by 4 times x by y. Now, if we want the tangent to be parallel to x axis, then for the tangents to be parallel to x axis, what should be the slope? The slope must be 0, because slope of the line x equal to constant, the slope of the line y equal to constant is 0. So, if we equate the slope to be 0, we get x equal to 0. So, therefore, we get x equal to 0 for the tangent to be parallel to the x axis. Putting x equal to 0 in the equation of the curve, we get, so x is 0 plus y square by 9 is equal to 1. This implies y square is equal by 9 equal to 1. So, y is plus or minus 3. So, 0 comma 3 and 0 comma minus 3 are the points where the tangents are parallel to x axis, which we also observed by looking at the graph of this ellipse. So, 0 comma 3 and 0 minus 3 are the points where tangents are parallel to the x axis. Now, for the second part, if the tangent is parallel to the y axis, the slope must be infinite. So, if we look at this dy dx is equal to minus 9 by 4 x by y, we must have y equal to 0. So, therefore, y is equal to 0, which will imply x square by 4 is equal to 1. So, x is equal to plus minus 2. Therefore, 2 comma 0 and minus 2 comma 0 are the points where the tangents are parallel to the y axis. This again we have seen from the picture that at minus 2 comma 0 and 2 comma 0 the tangents are vertical lines. Okay, so, the next problem you need to find the equation of the tangent to the curve y is equal to x minus 7 divided by x minus 2 times x minus 3 at the point where it cuts the x axis. So, first we need to find the points where this curve intersects the x axis. So, putting y equal to 0, we get x equal to 7. So, the curve cuts the x axis at the point 7 comma 0. Now, we will find the slope of the tangent line. For that we need dy dx. So, dy dx we can use the quotient rule. So, we have the derivative of x minus 7 times the denominator x minus 2 times x minus 3 minus x minus 7 times dy dx of x minus 2 times x minus 3 divided by the denominator squared. And this is equal to the derivative of x minus 7 is 1. So, we get x minus 2 times x minus 3 minus x minus 7 times dy dx of x minus 2 times x minus 3, this is nothing but this is x square minus 5 x plus 6. So, the derivative is 2 x minus 5 divided by x minus 2 squared times x minus 3 squared. Now, note that we have to find the slope at the point 7 comma 0. So, if I put x equal to 7 in this second term here is 0. So, we only get, so the slope of the tangent at the point 7 comma 0 is m is equal to dy dx at 7 comma 0, which is equal to 7 minus 2 times 7 minus 3 minus 0 divided by 7 minus 2 squared 7 minus 3 squared, and this can be cancelled. So, this is 1 by 5 times 4. So, 1 by 20. This is the slope of the tangent, and now we can easily write the equation. Therefore, the equation of the tangent at 7 comma 0 is y minus 0 is equal to the slope 1 by 20 times x minus 7, or 20 y is equal to x minus 7. Okay, so, the next problem we will look at where the curve is given in parametric forms. So, here we will try to find for the normal, find the slope of the normal to the curve x is equal to a cos cube theta, y equal to a sin cube theta, at the point where theta is equal to pi by 4. So, here the only thing is that we are not given y as a function of x, y and x are given in terms of the parameter theta. So, to find dy dx we can use the chain rule. So, the derivative, if we find dx d theta, this is equal to 3a cos square theta, and then we get minus sin theta, and dy d theta is equal to 3a sin square theta times cos theta. So, we have calculated the derivative of x and y with respect to theta, and this implies dy dx is equal to dy d theta by dx d theta. So, this is equal to 3a sin square theta cos theta divided by minus 3a, this is cos square theta times sin theta. So, we can cancel 3a and then 1 cos theta sin theta. So, what we get is this is equal to minus of tan theta. So, dy dx is minus tan theta. So, therefore, the slope of tangent when theta equal to pi by 4 is m equal to minus tan pi by 4, which is equal to minus 1. We want the slope of the normal. So, therefore, slope of the normal is equal to 1, because normal is perpendicular to the tangent. So, the slope is 1. Okay. The next problem, find a point on the curve y is equal to x minus 2 squared, at which the tangent is parallel to the chord joining the curve joining 2, 0 and 4, 4. So, these 2 points are on this parabola y equal to x minus 2 squared, and we need to find the point where the tangent is parallel to this chord joining these 2 points. So, first let us calculate what is the slope of the chord joining 2, 0 and 4, 4 is m equal to y 2 minus y 1 by x 2 minus x 1. So, 4 minus 0 by 4 minus 2, which is equal to 2. So, this is the slope of the line joining these 2 points 2, 0 and 4, 4. So, therefore, because we want the tangent to be parallel to this, the slope of the tangent is also equal to 2. Now, if we look at y equal to x minus 2 squared, this implies dy dx is equal to 2 times x minus 2. So, if we want the slope to be equal to 2, we get this equation, which implies x minus 2 equal to 1, which implies x is equal to 3. So, we get x equal to 3, and putting x equal to 3, we get y is equal to 3 minus 2 squared, which is equal to 1. Hence, the point is 3, 1, where the slope is parallel to the chord joining these 2 points. Okay. So, we have seen some problems say, on finding the slope or equation of tangents and normal at some point on the curve. Next, we will look at application of these to find approximations to the value of function at some point. So, application of the tangent line to approximation. So, let me explain what we want to do. So, suppose we have some curve y equal to f of x, and suppose we have a point here which is x comma y. So, this is the point P which is x comma y. Now, let us look at another point on this curve where this x coordinate is some x plus delta x, and let us call the y coordinate here as y plus delta y. So, this is the point Q x plus delta x and y plus delta y. So, here we have y is equal to f of x and y plus delta y is f at x plus delta x. So, suppose it is easy to compute f at x, but not so easy to compute f at x plus delta x. What we want is we would like to approximate f of x plus delta x by some value which is easy to compute. So, what we do here is we approximate it by the tangent line. So, let us look at the tangent line at this point x comma y, and then if we look at this point here, this point the x coordinate is, let me write this point as r, its x coordinate is x plus delta x, but now the y coordinate here will be L of x plus delta x, where L x is the equation of where y equal to L of x is the equation of the tangent at p x y. So, because we know how to calculate the equation of this tangent line, we can calculate what is L of x plus delta x. So, that will give me this value which is here. So, instead of getting this y plus delta y, we will get this value which is L of x plus delta x. Now, suppose this delta x is small. So, if we take the limit as delta x tends to 0, then this f of x plus delta x minus f of x, this divided by delta x if we take, this limit we know approaches f prime at x. Right. This is the definition of the derivative, that this difference approaches the derivative at x. So, what we are doing is so if delta x is small, then the approximation L of x plus delta x for f of x plus delta x is not too bad. So, what let us write the equation. The equation of the tangent at p x y is given by because I am using y here, let me write this as capital Y minus y equal to f prime x is the slope of the tangent line times capital X minus x, that is capital Y is equal to y plus f prime x times x minus x. So, at x equal to x plus delta x, capital Y is y plus f prime x times x minus x is delta x. So, hence the linear approximation is, what we are doing is f of x plus delta x, this is being approximated by y is nothing but f of x plus f prime x times delta x. Note that this is not exactly equal to, we are approximating this. So, there is some error in calculating this. So, now we will look at some example. Example 1, we want to approximate square root of 36.6. Of course, you must have learned method to calculate the square root of any number. So, this can be calculated, but we want to approximate this. So, what we do is, first you have to choose what is f of x. So, we take f of x equal to square root of x. We want the value of this function at 36.6. Now, if you see that if we take x equal to 36, then the square root of 36 is equal to 6. So, we take f x equal to this, and if we take x equal to 36 and delta x is equal to 0.6, then what we want is, we want f of x plus delta x. So, what we know is that f of x plus delta x can be approximated by f of x plus f prime at x times delta x. Now, what is f of x? Is the square root of 36 plus f prime x is 1 by 2 square root of 36 times delta x is 0.6. So, this is equal to 6 plus 1 by 20, which is equal to 6.05. So, what we are calculating, thus square root of 36.6 is approximately equal to 6.05. Though this is not exactly this, there is some error involved here. Let us look at one more example. So, note that in the previous one, square root of 36.6, there is a method to calculate square root. Now, suppose I ask you to compute the value of cube root of 25. Now, this is not easy to calculate exactly. So, again what we do is we take the function f x equal to cube root of x, and then f prime x will be 1/3 x to the minus 2/3, and then we take x to be equal to, now we have to look for the value near 25, for which calculating cube root is easy. So, the perfect cube which is near to 25 is 27. So, we take x equal to 27 and we want x plus delta x to be equal to 25. So, that is we take delta x to be equal to minus 2, and then cube root of 25 is same as f of x plus delta x, which we will approximate by f of x plus f prime x times delta x, which is equal to cube root of 27 plus 1/3 and 27 to the power minus 2/3, and delta x is minus 2. So, cube root of 27 gives me 3 minus 2 by 3 and 27. So, this will give me 9. So, 3 minus 2 by 27, so which is equal to 79 by 27. So, cube root of 25 is approximately equal to 79 by 27. We can also use this to approximate rate of change of quantity. So, let me do one more example. The radius of a sphere is measured as 9 centimeter with an error of 0.03 centimeter. Find the approximate error in volume. So, we have a sphere, the volume of the sphere is given by 4 by 3 pi r cubed. What we are given is r is equal to 9 centimeter, delta r is 0.03 centimeter. If delta v is the error in volume, this is equal to V at r plus delta r minus V at r, and we have seen that this can be approximated by the derivative V prime r times delta r. So, what we do is we just calculate, so therefore, approximate error in volume is equal to V prime r times delta r, which is equal to V prime r is 4 pi r square times delta r, and then you put r equal to 9. So, this is 4 pi times 9 square times 0.03, this much centimeter cube. So, this finishes our lecture on applications of derivatives. Thank you.